Every device you own processes information using a flat, linear string of ones and zeros. A switch is either on or off. A coin lands on heads or tails. This binary chain is reliable, but it forces complex problems into a rigid, mutually exclusive sequence. Quantum computing functions differently. By using superposition, a system can hold multiple overlapping states at once, performing calculations across a vast web of possibilities simultaneously. But there is a physical bottleneck. Maintaining these delicate, overlapping states currently requires million-dollar hardware and sub-zero vacuum chambers just to keep the qubit stable. These environmental requirements keep quantum processing locked inside elite laboratories. For the local economies that rely on responsive edge computing, these massive, supercooled mainframes are practically non-existent. Seeking to bridge this gap, inventor Rupesh Malpani developed the Qxbin framework. His goal is to create a functional, personal qubit simulator that operates at standard room temperature. To achieve this, the framework uses hardware you might find on a standard desk, the analog dynamics of a coin toss, a magnetic keyboard, and a grid-based punch card. Success in this area would shrink the logic of a sub-zero quantum lab into a form factor that is desktop accessible. The framework starts with a simple analogy. Once a flipped coin lands flat on a table, it has a definitive result, either heads or tails. In computing, that is a standard binary bit. But while that coin is still in the air, wobbling and spinning, it exists in a state of probability. It is heads and tails at the same time. To capture that wobble as data, the framework utilizes Hall effect sensors found in magnetic T-boards. While a mechanical switch only registers an on-off click, a Hall effect sensor measures the continuous magnitude of a magnetic field as a key moves through its travel. By tracking those analog magnetic nuances, we can take a multi-dimensional probability state and input it directly into a device as a measurable value. Once that analog probability is captured, it has to be organized. This is where the framework replaces the flat binary chain with a binary probability matrix. These handwritten schematics show the shift. Instead of a single string of numbers, the logic maps into a spatial grid capable of holding multiple coordinates simultaneously. The math behind this matrix uses fractional bases, symbolized here as I over O and O over I. By raising these to integer exponents, the system can record the specific weight of a superposition at any point on the grid. Those mathematical coordinates are then physically recorded onto a grid-based punch card format printed on magnetized paper. By linking those magnetic sensor inputs to this spatial matrix, a classical machine can read and process superpositions that would normally require a quantum processor. This effectively translates abstract quantum mechanics into a physical coordinate system that standard hardware can understand. This isn't just a conceptual exercise. The framework has been empirically validated, producing probability results that match standard quantum simulators. This validated logic is now moving into the real world, specifically the dense environments of Indian street kiosks. A startup called pikk.company is deploying this framework through Pick-stop hubs. These units function as localized data pods that don't need a constant connection to a central server to perform complex tasks. Because the Qxbin logic is so efficient, these kiosks can handle edge computing tasks and manage EV charging infrastructure directly on the street corner, solving the bottleneck of distant data centers. For a small business owner, this means access to localized AI and logistics optimization that was previously the exclusive domain of enterprise data centers. By using localized sensors to track power demand and foot traffic in real time, a single kiosk can coordinate EV charging schedules and inventory without external help. This converts the high traffic density of a market into a structured, self-managing local network. The Qxbin framework proves that high-level processing power doesn't always require bigger, colder mainframes. It is about making the math accessible, so the same efficiency found in a research lab can be used to grow a business on a street corner.